Welcome back, physics fans, for our fourth lesson in electrostatics. And I know we have good potential here. It's going to be called potential difference, also known as voltage. The electric field, we know, tells us that the newtons of force per coulomb placed at that point. So it's kind of like gravitational field, right? If we have a place that's near the Earth, here's the Earth, and that pulls down gravity. If we put an object in there, it's going to feel a force down there. But there is actually no object in there to begin with. It still has the gravitational field strength in there, and it has the potential to add a force there. And that's the newtons of force will be how much mass you put in there, and if it's electric field that's there, it's how much charge you put in there will get a force in there. Okay? And now for energy, there's an analogous concept that tells us the joules of energy per coulomb placed at that point. Okay, we talked about that in lesson 3. Okay, so if we have a mass here, it will have potential energy. Okay, and because if it was gravity, this would be the mgh if you want, or the kgmm over r, negative. But this location here is all about that. It's a location, and if I have no mass in there, it still has the potential to have potential energy. Okay, it still has the potential to have potential energy. And then if we have a big positive charge here, and I have this location here, if I put a charge in there, if and when I put a charge in there, it will have potential energy. The amount of potential energy it gets will be kqq over r, but I haven't put that charge in there yet. This locality has the potential to have potential energy. The potential to have potential energy. Okay? And this quantity is often called potential. Okay? And it's also referred to as voltage. Now, not really, voltage is the change in potential. It's a potential difference. Okay, and we give it a term V. The units of potential are joules per coulomb. It'll have so many joules of potential energy depending on how many coulombs of charge we put in this location. This is still a location here. Okay, and we have to be careful not to confuse joules per coulomb with just joules. Okay, so I'm just going to write down a couple formulas and we'll get going with them right away. Okay, but you might already have seen it here. As soon as I got rid of the Q there, what was left is the formula that we're going to have second. So that will be KQ over R. It's missing the other Q because that's the possibility of putting another charge in that location to get the energy. So V is KQ over R, and that is the potential, and it's measured in joules per coulomb. Q is the charge that's creating that potential. Okay, so we have a charge that's creating that potential field, and that's going to be radiating it away. That's the E field, but that's also the potential field, the voltage field, if you want to talk about it. It's the potential to have a voltage, depending on what charge you put there. Okay, so we'll use this formula, then we'll come back and develop this one in a moment. Here's a 7-mark provincial exam question. The potential difference in moving from position A to position B. So delta VA to VB is in the diagram below is 400 volts. Determine the size and polarity of the charge. So we have a voltage at this location and a voltage at this location. And they want to know, what is the charge? We know that moving it from this location to this location has a difference in voltage of 400 volts. So going from final minus initial, VB minus VA is going to equal 400 volts. So KQ over R minus KQ over R is equal to 400 volts. We have a different Q. No, it's the same Q. It's the same Q. In fact, we don't know what that Q is. That's what we're trying to determine. We have the different R's and we have the constants. The final R is 9 meters and this R is 4 meters. So we end up being 9 meters away at B, and at that we is 4 meters away. Okay, I'm just going to go over to the side here instead of ruining my diagram over here. So it's 9 times 10 to the 9th Q divided by 9 minus 9 times 10 to the 9th Q divided by 4 is equal to 400. So the only unknown we have in there is Q. Okay, and there's fractions and stuff like that, and I know 7/5 of the students don't understand fractions, but we'll just take out the Q by itself, and we have 9 times 10 to the 9th, and then in here we have 1/9 minus 1/4, and that's equal to 400. Okay, all I've done is taken the Q out and also taken out the 9 times 10 to the 9th. So it's 1/9 minus 1/4 is that bracket. So 1/9 minus 1/4, and now I have to reciprocate it back. Well, not square it. I have to take this number, reciprocate. Oh, goodness gracious, 65. So this bracket is this number. Yeah, we could have done fractions, but so this Q 9 times 10 to the 9th, and this bracket 0.1015384 is equal to 400. So 400 divided by these two numbers will be the Q. So 400 divided by 9e to the 9th, and also divided by that number there, and we get Q is equal to 2.89 times 10 to the negative 6 coulombs. Okay, that's the charge. 7 marks. It looks like a little bit of work there. It's not tough. At this point, it became the math. And in fact, the marking on this provincial exam question, if you get up to here and start plugging in the numbers, so if you get this line, I believe you got already 5 out of 7. Okay, let's develop that second equation over here. And this, we'll do one example with it and then call it quits for this video. That we're going to be getting that the potential energy is Q times V. So V is equal to the work done. So it's often done as the change in potential energy all over Q. This is joules per coulomb units. And so how much work you've done per coulomb is going to be the potential. Okay? So V is equal to the potential energy over Q is our formula. Gonna I'm not going to develop that formula any further, but here's a multiple choice question on a provincial exam for 2 marks. What is the final speed of an electron accelerated from rest through a potential difference of 750 volts? Okay, so we have that the voltage is equal to the change in potential energy per charge. Okay, so we have the voltage, we're going to get the potential energy. So the change in potential energy is equal to QV. Okay, that's the one that I memorize. The change in potential energy is equal to QV. We have V, and we have the Q. The Q of the electron is the elementary charges, which is 1.6 times 10 to the negative 19th coulombs. And that's the change in potential energy. Where does that potential energy go? It goes into kinetic energy. That'll be that. So we have this is equal to the change in kinetic energy, which is 1/2 mv squared. So we isolate for v, and we get 2 v's in here. So this is why you'll see me always writing voltage with that funny looking v. Right? It's a capital V, but sometimes when you're scripting things down, you can't see the difference between a small v and a big V when you're scripting it down on your page. So when I write down voltage, I put the little funny hat lines on the top because we have V for velocity and V for voltage. Okay, so V is equal to, let's just leave it as V squared, leave V squared over here. It'll be 2Q voltage all over the mass. Okay, this is so very common. You'll get to this stage many times because we put a charge through a voltage, a potential difference, to accelerate it. How fast does it go? It it is always this speed, 2qv over m, all square rooted, because it's the potential energy, which is qv, which is changed into kinetic energy, which is 1/2 mv squared. So this is going to be 2 times the elementary charge, 1.6 times 10 to the negative 19th. The voltage is 750 volts. Okay, so you'll now really understand, because of this question, why I do that V that way all the way along. You've seen it already all the way along. It's just the same way that I always say in circular motion, centripetal. No, I call it centripetal, because you can't really hear my voice say the difference between centripetal and centrifugal. So I mispronounce it on purpose. Kind of like when I do watts, I never do W as just watts. I'll put in the whole word. Why? Because this W is also work. So if you leave it as 10 watts, so someone might go, well, that's 10 times the work. So I do things after working in physics here for teaching it for more than 30 years, just a little tips so that you don't make mistakes. And that tip is when you write down V for voltage, make it a different V than used for in the formula for V for velocity. So the mass of an electron is 9.11 times 10 to the negative 31st. Do you have to have them memorized? It's on your formula sheet, so the answer is no. Okay, then I have to square root it to get that velocity. So let's just plug it into our calculator, and we're almost done the whole video here. Okay, so it'll be the square root of 2 times 1.6 e to the negative 19th times 750 divided by 9.11 e to the negative, I didn't do 911, I did 977, 911 e to the negative 31st. And I get 1.623 times 10 to the, move it over 3, move it over 3, and another one, this will be times 10 to the 7th meters per second. Feet, go on. Thank you very much. Subscribe. Enjoy my videos, I hope. Leave a comment if you do. If you don't like them, don't leave a comment. And smash that like button. Bye-bye.